I just want to have full disclosure. I am recording this session, and the reason I'm recording this session is because I'm trying to do better at getting all of my lessons online, because it seems like we are getting more and more people that are being quarantined, and I want to make sure everybody has the opportunity not to fall behind when they're at home. Because if you're at home quarantining for 14 days, and you're expecting to come back, not do anything at home and catch up, that is not going to happen. So this is my way of trying to, help people out. Today's question is, how do we study stars from Earth? I can't say, Ryan, go to Proxima Centauri. Here, fill this up. Bring me back some of the plasma. It would take him like 10,000 years to get there, right? That's impossible for me to do. So I cannot send Ryan out. How then do I study the stars from our location on Earth? Good question, Mrs. McGrain. Ryan, what do you think? How can I get those stars studied from Earth?
Telescopes?
Very good. When I look through a telescope, what is it that I am viewing? Don't say the star. What from the star? What's coming to you from the star through that telescope?
The light?
Yeah, man. We're studying the star's light. So let's go ahead and write that down. How do we study stars from Earth? We have the star's light coming to us. So we study the star's light that reaches us on Earth. How does light travel? How does energy travel?
In waves.
Good. Light travels in waves. By studying that light pattern, by studying the visible light pattern, by studying the visible light pattern from stars, from stars. What did we learn yesterday in our notes that we could learn about the stars? Light travels in waves by studying the visible light pattern from stars. Dun, dun, dun. What do we study? Eduardo, where's your glasses?
I left them at home.
Dang it! I'd let you borrow mine, but I don't think that works for you. What do you think? By studying the visible light pattern from stars, what did we learn yesterday? We can figure out about what's happening in that sun, that star. I know you know this. You're killing me. How would you find out? If I said it's from yesterday, what's a tool that you could use? You could use what? Man, I love you. You could use your notes. So if we look at the spectrum of light, and we notice that there's pieces of the light missing, what does that mean is going on in that star? There's nuclear fusion, which is creating what? What does nuclear fusion create other than light?
Plasma?
What?
Plasma?
Plasma is the star.
Okay.
What is nuclear fusion creating other than the light? Nuclear fusion creates light.
And heat?
And what, helium or heat?
Heat.
Heat is true, but I'm looking for helium. New elements. Those elements are absorbing part of the light. So by studying the visible light pattern from stars, we can discover what elements are in the stars. We can discover what elements are in the stars. Woo! That's awesome. Nice job. So today what we're going to do is we're going to start looking at those special light patterns that are put off by elements when we excite the elements. So we're going to go ahead and excite some elements in here. back there, and we're going to see what kind of light they put off. I'm going to remind you of what it is that I'm talking about by looking at yesterday's notes. So I'm going to go to, I believe, the bottom page of this note sheet, which is reverse, where is it? There it is. All right, so do you see this? This is the emission spectrum. When you superheat an element, in this case they say a gas, it's going to release certain wavelengths of light. When those wavelengths of light are combined, it's going to have a certain color pattern of that element. And if you see that, you're going to say, oh my gosh, that's copper. Has anybody ever thrown copper into a campfire? Oh, well, you're going to see it today, because today we're going to burn copper. Okie dokie, so let's go ahead and look at our lab. We're going to set this sun gun up. I am going to ask you to practice your active reading today. If it is something that you are not comfortable with, that's okay. But reading out loud is a skill, and it's something that, you can practice at. I know you don't have your glasses in the back, but do you want to read the first paragraph in front of you? So this lab is called What Can We Learn from a Star's Light? This is an investigation that we're going to be doing. Eduardo, do you feel comfortable?
Sure.
Great. Could you please read the first one? I'm going to stop periodically, and we're going to underline and talk about some things. Go ahead.
The astronomer Carl Sagan once said, "We are made of star stuff." He was referring to the fact that every element in our bodies and the world around us was once created deep inside the star.
Pause. Everybody underline that. So that was a question that I asked you yesterday at the beginning of our note session. Why is it that some people say we are made of star stuff? Here is the answer, just in case it's a question on the exam. Every element inside of your bodies and the world was once created inside of a star. If a star didn't live and then die, you would not be here today. So you literally are made of star dust. You're superstars. All right, Eduardo, go ahead.
Know the process of nuclear fusion. Stars create all of the elements in our universe over the course of their lifetime. Scientists have theorized
Good.
that that the smallest element in the universe, hydrogen and helium, were created during the Big Bang.
Okay, pause. Everybody circle hydrogen and helium, and then I want you to underline were created during the Big Bang. So those were our first two elements. Not created in stars, right? Helium now is, if it's just hydrogen and hydrogen, but hydrogen and helium were the first elements created during the initial Big Bang. Just in case that's a question on the exam. Okay, Eduardo, bring us home.
Over time, stars formed, and as they heated up, it became so hot that some of the atoms would collide and stick together, releasing energy and creating new elements in the process. This is called nuclear fusion.
Good, and we've got a picture right here of nuclear fusion. And I don't know if you remember when we were taking our marshmallows, I said, hey, it's a little bit more complicated than what we're drawing. This is what I'm talking about. You have a hydrogen with one neutron, a hydrogen with two neutrons. Through fusion, you get a larger element, a neutron pops out, and then you get energy. Could you please write this word photon where it says energy? Photon. And then for our purposes, we're not going to worry about this extra neutron. We're not going to worry about the extra stuff. In a 9th grade classroom, I want you to know two nuclei come together, you get a larger element, and you get light and heat. That's all we're worried about. Fabulous. Good job, Eduardo. Can somebody else please read the second paragraph for me? Go ahead, Carter.
How can scientists study stars that are millions of light years away? For very distant objects, direct observations are impossible. We can't take a sample from something so far away. In fact, it would take over 10,000 years of space travel just to reach the furthest star we can see in the night sky. That's over 20,000 years round trip. Plus the time for the research, that's not a very efficient use of time. Instead, scientists must make more indirect observations to learn about space.
Great. Let's go ahead and underline indirect observations. In science, a lot we do indirect, we collect indirect evidence. Direct evidence would be like if I said, Nessa, go outside with this thermometer and tell me what the temperature is right now. That's direct observations of the temperature. If I said, Nessa, go back 5,000 years and tell me what the temperature was. She can't do that. So we have to find indirect evidence for what the temperature was like 5,000 years ago. We look at things like what plants were growing. Do we have fossils of the plants that might have been growing at that time? What do the rings in a tree look like from 5,000 years ago? That's indirect evidence. We can't go there and directly get it, so we have to look for indirect. I can't send Ryan directly to the star and say, here, fill up this bottle with plasma. So we're trying to figure out what's in a star by indirect observations, looking at the light coming from the star. Nice job. All right, well, this looks familiar. What is this a picture of? What is this picture of, Riley? The EM spectrum. Would you like to read this? Okay, go ahead, Riley.
Most of the information astronomers use to study objects in outer space comes from electromagnetic radiation collected by instruments such as telescopes. Electromagnetic radiation ranges from radio waves, microwaves, infrared radiation, to visible light, ultraviolet light, X-rays, and gamma rays. Many of these are used in our everyday lives, even though we can only see a tiny portion of them. Instruments attached to a telescope can measure, record, and analyze all this electromagnetic radiation. An instrument called a spectrograph takes the light and breaks it into all its pieces to create a spectrum or spectra. Scientists analyze the spectra of stars, galaxies, and other celestial objects to study what they are made of, how big they are, how hot they are, what color they are, or how they're moving. In this investigation, we will use light as a tool to learn about stars and elements.
Yes, so we are going to use light. We are going to light up some elements in the classroom. We're going to see what kind of colors they release. So remember, a spectra or spectrum is just a range of light energies. So we are going to excite some elements so that they will release their special light fingerprint, if you will, okay, identification. So that when you see it, you'll be able to like, oh wow, that's copper, oh, that's lithium. We can identify that element. So we are going to do that right now. You please turn the page and look at your next page. This is the objective that I'm going to go ahead and read to you. You do not have this. You should have a big table that shows up on your piece of paper. You will observe the light released by burning different elements, and you're going to use your observations to determine the identity of an unknown sample. Okay, so first we're going to study known samples, what the color of lights are. Then we're going to use that information to identify an unknown sample. You're going to try to guess what it is. You will then make a claim about how scientists can use information from light to learn more about elements. That's all we're going to be doing today. The next day, we're going to compare the atomic absorption spectrum. That sounds really super scary. It just means we're going to look at the spectra, or the range of light energy, that a certain atom, or an element, is absorbing. That's all that means. We're going to look at 5 different stars, and then we are going to try to figure out what elements are going to be in that star. That's going to be on Friday. So for right now, let's go ahead and look at the table you are going to be filling out. Oops, sorry. Let's get rid of all of that because your observations, I want to be your observations. So we're going to look at sodium, calcium, blah, 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 blah. And cross out this last unknown sample. We don't have 3 unknown samples. All I have are 2 unknown samples. I'm going to now mute this as far as not being able to see it. I'm going to get my goggles. I'm going to head on to the back, and I'm going to need you, please, to turn yourselves so that you can see what's going on in the back. I have matches. I think it's going to be very dark. Okay. I'm going to attempt, let's turn this around. I should be able to just, shouldn't I be able to just turn this like the other way? Can you only videotape in one direction?
Yes.
Really? Let's. Thanks. think it's part of. All right, let's see if we can get this lit. Ew, don't burn myself. Okay. Let's see if we can see what we're doing. Yeah, you can see that pretty well. All right, so we are going to have some chemicals. I need you to tell me what's the first one that I'm looking for, please. Sodium. I don't know if I've got it in the right order. Yep, sodium. All right, so here's sodium. We are going to, I'm going to try to attempt to light the chemical or the element, not the sticks. You tell me what you see for color. So what do you think? Orange, yellow, you think it's an orange? Then write down orange in the color. As far as extra observations, if you feel like it's a red orange, a yellow orange, you can do that. And I can come back and look. Do you want to see it one more time? And I can come back and show you other ones. What's the next one, please? Calcium? So again, remember, we are looking at the emission spectra. Are these colors showing up? Can you see in here? Let's see if I can get, okay, there we go. I'm trying not to light the stick on fire. This looks orange, but it looks a little different than the other orange. Doesn't it? Or does it still just look orange? Write down orange, and then I will go ahead. Oops, that's on fire. No, 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 no. Out, 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 out. Okay, this is sodium one more time. That looks a little bit more yellowy to me. I'm not saying it's yellow, but it looks like an orange yellow. And then this one is the calcium. This one looks just, I don't know why, just a little bit more red, orange. But if you just want to say orange and orange, then you just say orange. Okay, that was, so, what's the next one? Copper. What color do we think this is going to be? Oop. Good? Oop, I don't want it to be on fire. What color do you think? Green or teal, or is the next one? Oh, this is my favorite. I should have favorite elements, right? Well, then this would be my favorite. It's not really red. Yeah, it's like a very vibrant magenta or hot pink or very pretty. Okay, and then this one is barium. Yeah, it's definitely like yellow. Somebody said the other day it was kind of like a green yellow. But definitely it's got that yellow quality. All right, and then the last one that I have here, I've got one more that is not on the table I want to show you, but this one is strontium. It doesn't really look like lithium. It's got that same reddish color, but it's almost like a red orangey, or like a more red color, rather the other one was almost like a pink sort of red. Anyway, that's strontium. All right, the last one I want to show you is not on your chart, but I think it's pretty. it's potassium. And so this one I just think is a pretty color. It's like a lilac kind of light purpley. I just think that's lovely. So that's potassium, not on your chart. All right, are you ready to see the unknown? I want you to know that I only have one jar here, and yet you have two unknown one, and you have an unknown one and an unknown two. That's because in here I have mixed two different colors. I've mixed two different elements. So you need to look at what you're seeing and see if you can figure out what the unknowns are. I don't care what you mark as unknown one or unknown two. Okay, I don't care. That's up to you. Oh, that's fire. No, no, no. Good? Okay. So let's go ahead and turn this around. Wave, Carter. Wave. Yep, I can see it. Oh. Well, kind of are. All right, I'm going to go ahead and wash my hands because that's proper technique when we are dealing with chemical substance. Always want to make sure you wash your hands afterwards. Notice, what did I have on my face?
Goggles.
Yeah, because Mrs. McGrain likes to see my beautiful students, and I don't want to lose my eyes ever, and I don't ever want you to lose your eyes. So it's always important to use our goggles. Okay, so I am not interested in what you thought the colors were. These are what you thought, okay? These are your observations. So there's no right or wrong answer here at all. This is you as a scientist collecting data. All right, so let's go ahead then and look at the first question. It says, what is the identity of unknown sample number 1? So whatever you think sample number 1 is, that is going to be what you're going to write down. And you're going to write in complete sentences. Notice I gave you a start there. I think unknown 1 is. So start there. Whatever you think based on the other colors that we saw. I think unknown 1 is. Don't even worry about the because right now. What colors did you think were in the samples, the unknowns? Okay, green. What element do you think that was? Okay, so then what was another color that you saw, Sunny?
That pink color.
That pink color, and what one was that?
Lithium.
Lithium, okay. Does anybody think that there might have been another alternative? Maybe it wasn't lithium, maybe it wasn't copper. What did you see, Enzo?
What different colors?
Well, just because of the color, what colors did you see, and because of that you thought it was this element?
Well, I thought it was like copper as well too.
Okay. Okay, and then did you see another color that you thought maybe? Because there was, huh?
I saw red.
You saw red? So red, what two colors could it have been if it was that red? Or what two elements could it have been if it was that red? Look down at what the colors were for the, if it was red, what two possible elements could it have been?
Lithium
Uh-huh.
and strontium.
Right, could have been lithium or strontium. Which one are you leaning towards, Enzo?
Lithium.
Lithium? Okay, so we have, what is the identity of unknown sample 1? I think unknown sample 1 is, now you're going to do because. Let's think about what would be a good because. Before you write anything, because why? Because why? Sunny?
Because it was showing a color that was like also shown on like, if you were saying copper as one of them, you could like because copper showed green, and when you put the unknown 1, it showed green.
Okay, showed green when we did what though? Don't forget to tell me what did we do. It showed green when we burned it. Okay, so add that. If you think unknown sample is 1, you can say, I think unknown number 1 is copper because when we burned the known sample of copper, it also turned green. You're using complete sentences. You're writing like a scientist. I think unknown 1 is copper because when we burned the known sample of copper, it was also green. Use that same format for what is the identity of unknown sample 2. I think unknown 2 is whatever, because when we burned said element, it also turned, or it was blah, blah, blah. It burned the same color as known sample lithium or strontium or whatever the heck you think you saw, write it down. Cross out number 3, please. We are not doing that one. And then when you are ready, turn the page. Ready? I'll give us one more minute. Oh, God, these times are so not ready. All right. Oh, I said I'd give you a full minute. Okay, wrap up your final thoughts. Let's look at part 2. How can we identify elements in an unknown sample based on the light they emit? We're going to start with this sentence starter. I think that we can identify elements in an unknown sample based on the light they emit by, write that down. I think we can identify we got the sentence starter right there for you. I think we can identify elements in an unknown sample based on the light they emit by first doing what? By first doing what? We were identifying elements on an unknown sample based on the light they emit, but first we had to do what?
Burn
Burn what?
the chemical or,
Burn what, the known or the unknown chemicals?
oh, no, the known.
The known. I can't figure out what an unknown is before I know what the color is going to be from a known sample. Okay? So I think we can identify elements in an unknown sample based on the light they emit by first observing the color emitted by different known elements. By first observing the color emitted by different, oops, that's how you spell it, different known elements. And then comparing the color to the unknown element. I think we can identify elements in an unknown sample based on the light they emit by first observing the color emitted by different known elements, then comparing the color to the unknown element. That is talking like a scientist. That is writing like a scientist. That is putting together a lab like a scientist. Pat yourself on the back. So good. So good. All right, now let's go ahead and look at our evidence. List 3 sources of evidence from the investigation to support your claim. In the evidence section, you should only describe the evidence. We're not going to explain how it's related, like, ooh, the color is blah, blah, blah. We don't care. We don't care about what color it is. We just care that we saw a color. So if we think one of the samples was copper, we could say evidence 1 would be, did anybody think the unknown was, I'm just going to say copper was the unknown one for 1. So evidence number 1 could be the color of unknown 1 when burned. The color of unknown 1 when burned. That could help us figure out what unknown 1 was. Our evidence was the color of unknown number 1 when burned. Could we use this same evidence for unknown number 2? Darn straight, write that down. Second piece of evidence, the color of unknown number 2 when burned. Or I guess you could say my first source of evidence is the unknown color. Now, evidence 3 would then be what? If we know what the color was for unknown 1, we know what the color was for unknown 2, what would be another piece of evidence that we need in order to figure out what 1 and 2 were? Think! Rather than me give you the answer. Think! If we're trying to figure out what 1 and 2 are, we've got one piece of evidence that says, well, I burned number 1 and it turned a certain color. I burned number 2 and it turned another color. How would I then figure out what those are? What's the third piece of evidence we have to look at? The what? The known element color. That's right. So we would have to say the third piece of evidence, I think I spelled that wrong. Evidence is the color of the known elements when burned. Because then we are comparing. This is science. Do we know for absolutely sure what elements those were? I do, but I'm not going to tell you. You just have to figure it out based on what you observed. That's science. Is science then perfect? No. Does science sometimes make mistakes? Yes, because it's human. Human beings do science. Human beings can make mistakes. But based on the best evidence you have available and the observations you made, you determined what unknown 1 and unknown 2 was. And this is how you did it. So let's go ahead and write some reasoning. What do we get out? Is it 40? Just so that I'm making sure. Yeah, it's 40. How am I doing on time right now? Like 15? Fabulous. All right. So we're going to go ahead and do some reasoning here. We're going to discuss the source of our evidence. all in here. So we have to tie it together. My first source of evidence is a result from my investigation of unknown sample 1. During the investigation, unknown sample 1 burned whatever the heck color you want when I put it into the flame. I was able to determine that its identity was whatever element you think it was, because when I put that known element into the flame, it also burned that color. Do you see what I'm saying? We're reasoning it out. Are we good? Let's write it up. Discuss the source of evidence. My first piece of evidence. My first piece of evidence was, what was our first piece of evidence?
The color of the unknown.
Right, my first piece of evidence from the investigation. Okay, so my first piece of evidence was the unknown, number 1, I guess was what color? Was whatever color. Was blank color when burned. I was able to determine, did I spell determine or is there no N at the end? Oh, that's right. That its identity was whatever element you think it was. And we could say the reason for this is and then you're going to reason it out. The reason for this is when I put that element, when I put, and then you tell me whatever element that is, blank element, into the flame, it turned whatever color. My first piece of evidence was the unknown number 1, was blank color when burned. I was able to determine that its identity was whatever element you think it was, copper, lithium, strontium, barium. The reason for this was when I put whatever element, strontium, blah, 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 into the flame, it turned blank color. Okay. Now, we're not done yet. I know that every element has its own unique, should we say wave pattern or light pattern? Wave? How about we say wave light pattern? Wave light pattern when burned. Because of this, I was able to identify the element. Because of this, I was able to identify the element. That sounds exactly like a scientist would write it, because you're little scientists. Sorry, I said the fifth piece of evidence. It's supposed to be the first piece of evidence. The first piece of evidence was the unknown number 1 was blank color when burned. If you thought it was green, if you thought it was pink, if you thought it was yellow, put whatever color it was. I was able to determine that its identity was, and then whatever element you think it was. The reason for this, when I put whatever known element into the flame, it turned blah, blah, blah color. I know that every element has its own unique wave light light pattern when burned. Because of this, I was able to identify the element. Nice job. Thanks. Let's go ahead and turn the page. Notice it says discuss the second source of evidence. You would do the same thing that you did for unknown 1 with unknown 2. We're not doing that today. So let's just move forward, shall we? Let's look at part 3. Part 3 is all about what can spectra, meaning range of energy colors, tell us about stars. If you shine plain white light through a prism, like this prism, if I was able to have the sun shine and it shone just right through the prism, I would be able to see a spectrum of color, all the colors of the rainbow. We've got red, orange, yellow, green, blue, indigo, violet. And that would be the absorption spectrum. However, when you shine specific light, like a specific element, like let's say strontium, okay, if you would shine strontium's light, it would have a different kind of light pattern. And so if we look here, this right here, well, I'll just read what it says. If you shine plain white light through a prism, you will see a continuous spectrum with every color of the rainbow. However, when you shine a specific element's light through a prism, you will see an absorption spectrum, meaning a range of light that the element is holding on to. An absorption spectrum is unique to each element. Again, it's that unique pattern of light. Because each element is going to absorb unique and specific wavelengths of light. So just like the elements released or emitted a specific wavelength of light, they also absorb it. Because the element is absorbing that wavelength, we cannot see it on the spectrum. Instead, we see a black line. For example, the absorption spectrum for hydrogen shown below. Notice we should have a clean pattern, but we don't. We've got missing light, missing light, missing light, and missing light. So in the passage above, highlight or underline the sentence that describes why this light is missing. Why is the light missing? Read through, see if you can find it, and then we'll talk about it as a group. Why are there blank spots? Read up here. Do you think you found it? Okay, Aiden, where do you think it is?
The first about because the element is absorbing that wavelength, we cannot see it on the spectrum.
Okay, so he's saying where it says because the element is absorbing the wavelength, we cannot see it on the spectrum. So let's go ahead and back up a little bit more to give us a little bit more context as to what it is. So because each element is going to absorb a unique and specific wavelength of light, the element is absorbing that wavelength and we cannot see it on the spectrum. Let's underline all of that. Good job, Aiden. This next question is going to be for Marina. How many different wavelengths of light is hydrogen absorbing? All I'm saying is, how many black lines do you see? So we're going to write down 4. Good? It's going to be great. All right. Who would like to read this last paragraph for us? I love it when I look at you all and you're like, I'll do it. Every element has its own unique absorption spectrum. So just like every element emits a very unique pattern of light, every element also absorbs a unique pattern of light that we can identify it by. So does every other object that emits light. You also emit light, by the way. It's just in a range that we cannot see. This means that stars, galaxies, planets, nebulae, and all the other celestial objects, that just means objects in space, in the night sky have their own unique absorption spectrum, meaning that they absorb and hold on to a unique wavelength of light. We can use these spectra, these range of lights, to learn a lot about a celestial object. For example, look at the absorption spectrum for the sun, okay? Imagine a bunch of colors here. There are missing parts of the color. What? Who took the color? Well, in this case, hydrogen is holding on to some of the color. So we can compare it to the absorption spectrum for hydrogen. We can see that all the lines that appear on hydrogen's spectrum, this is the special signature of hydrogen, is also present in the sun. So notice this matches up, this matches up, this matches up, this matches up. So if we studied this fingerprint from the sun, if we look at the missing lights of the sun, missing parts of the sun, and we're able to distinguish that the specific pattern for hydrogen is in there, that tells hydrogen is in the sun. Is hydrogen the only element in the sun? No, because there's other missing wavelengths of light. So there must be other elements in there absorbing and holding on to that energy so that it doesn't get to us on Earth. So what do the circled lines on the spectrum tell us about that star? What does it tell us about that star in regards to hydrogen?
It has hydrogen.
Boom! It has hydrogen in the star. How much time do I have, Emma?
2 minutes.
2 minutes. Okay, so what I'm going to do is I'm going to show you a little video to get us started, and we are going to jump into where we were today. Tomorrow. Oh, sorry, you can't hear that.
Our only contact with the distant stars is their lights that journey across the universe to reach us, and encoded in that light is the key to understanding what the universe is made of. And it's all down to a particular property of the chemical elements. You see, when you heat the elements and you burn them, then they give off light, and each element gives off its own unique set of colours.
And that's what we did.
So this is strontium, and it burns with a beautiful red colour. Sodium is yellow. Potassium is lilac. And copper is blue. Each element has its own characteristic colour. It's this property that tells us what the stars are made of. But it's a little more complicated than simply looking at the colour of the light that each star emits. You can see why by looking at the light from our nearest star, the Sun. This is a spectrum of the light taken from our Sun, and at first glance it looks very familiar. It looks like a stretched out rainbow, because that's exactly what a rainbow is. It's the spectrum of the light from the Sun in the sky. But if you look a bit more closely, then you see that this spectrum is coloured in black lines. These
Alright,
are called
see you
absorption
tomorrow.
lines.
Thank you so much. Have a great day. Tomorrow we're going to study stars. Nope, I better shut off my video. Well, I hope you enjoyed the lesson. Ta-ta!